I'll make an effort to stay on schedule. Big thanks to the organizers for having me. I've had a blast so far, in part because, as Todd said, we get to meet people that we haven't seen in a while. But also, I think, I'm against anything Zoom-based these days. In-person meetings are the right way to go to talk and chat and argue. So my talk is on decision-making with information-theoretic constraints. That's kind of my take on, machine learning with information theory. It actually does connect quite well to quite a few things that we've heard about over the last few days. So I'm going to connect to what Tara presented on day one. I'm going to kind of piggyback on some of the comments Aaron made about, leaving distortion theory aside, or classical distortion theory aside for a little bit. And I'm going to talk about Chernoff information, like we heard from Sangamitra in the previous talk. I should first and foremost start by giving credit where it's due. So I've had really good students who've actually helped me, and if not done, most of the work around these topics. And so I won't go into the details, but they deserve a lot of credit. And, Todd, congrats on your newborn. I also have a little one now. So that's Adrien. He's a COVID baby. He was born 5 days before the lockdown. And he's doing RKHS during office hours to teach grad students what to do. All right. My second slide about credit where it's due. A lot of what we've explored in that space is very much motivated after I read two really cool papers. Well, technically three. So the sequential design of experiment paper by Chernoff, but also like more modern takes on that from maybe 10 years ago now. So there's a nice paper on control sensing for multi-hypothesis testing coming from the cornfields. And Tara, kind of had a similar take on that called active sequential hypothesis testing. And these things are kind of generalization of the sequential paper of Chernoff. And when I read them, it's kind of interesting that they connect actually control and machine learning and information theory in a nice way. And so I got kind of fascinated by these results. And very briefly, and not doing full justice to everything people have done, the problem is the following. So imagine, you have a kernel here that generates, samples that you can observe, and then your goal is to make a decision about a hidden parameter that governs that distribution. So the controlled sensing or active hypothesistic view of this says, well, there's also another input, which we're going to call U, that allows you to tweak that kernel. So you can actually take actions, and these actions can actually be dependent on your past observations. You can close the loop and adapt how you're going to probe to get samples. And the goal is to get an estimate of theta that is as reliable as possible, as fast as possible. There are lots of variations of that setup, right? You can say, I want to get exactly n samples. That's called the fixed length setting. And that's kind of, I think, the easiest one to connect to from an information theory perspective, because we're used to having like a fixed block length. But the best things you get are when you start allowing sequentiality, meaning you have a stopping time, you have a rule to decide when you stop probing, and then you replace your block length n by an expected stopping time, for instance. And then you can ask question, does it benefit me to be sequential versus fixed block length? You can also say, does it benefit me to actually adapt my probing as I get my observations? But generally speaking, the key quantity that people look at, and I'm oversimplifying a little bit here, is this notion that if you have a fixed set of hypotheses, let's say theta takes one of n parameters, you can look at the error exponent when you make a decision on theta, and you can measure the quality by taking the limit of large block length of the log of the probability of making an error with a fixed policy pi here divided by n. So it's kind of quantifying the error exponent, how fast you make that decision. So if theta is not taking values from a finite set, it takes a continuum of values. You have to enter the realm of Kramer-Rao bounds and whatnot. So I'm not going to talk about that today. And what motivated me with that is that this is actually a pretty powerful model that abstracts a lot of the problems we have with dealing with feedback and how to make decisions once we have past observations. Maybe not quite as sophisticated as what Todd was presenting this morning, but some of what Todd was presenting, the flavors are in these models. And the motivation for me was to say, okay, there are lots of problems in engineering where this model actually has a lot of things to say still. And so I'm going to kind of give you two vignettes of things we've thought about. So one was motivated by a really cool paper that's actually coming from the quantum world, where people were, coming from MIT actually, I think, where people were saying they've invented a covert radar, right? So you want to illuminate a plane that's coming, but you don't want the plane to realize it's being illuminated. right? Because that's one of the things, like if you watch military movies, right? Like the planes get simulated, they start evading and whatnot. That's when movies get interesting. But what if they can't detect, right? They're being illuminated. So they call that the covert radar. And I thought, that model might be a cool way to think about, this covert radar. But then you need to define, what does it mean to be covered? And so we're going to modify the problem a little bit, and I'll say more in a few slides, where you have to kind of look at it in two ways. There's potentially there's a closed loop which you control, that's a person operating the radar, but then there's an adversary who's being illuminated, and they also have to check, is something happening? Am I being illuminated? So you're trying to make a best decision, but there's a constraint implicit about what you can do to probe, because if you probe too high, you're going to be detected. So we can formulate kind of interesting games here. So I'll talk about that. And the second scenario I will illustrate is one that's becoming popular with all the folks doing 6G. I don't know what 6G is going to be. It's going to be a more expensive cell phone, I can guarantee you that. But they're talking about, convergence of different frequency bands. You can do communication and radar at the same time. And so if you think about that, it's kind of, if you believe that, my radar is a hypothesis testing problem, I'm trying to probe to figure out the value of a parameter. Now, the constraint that you have is that the probe, they also have to embed information. And so, by a modification of this canonical active hypothesis testing problem, you can try to embed this sort of reliability information theoretic constraint. So I'm going to try to highlight that. I kind of highlight, I think, what also the kind of the key technical challenges that one has to play with. But I won't go into a whole lot of details. So let me start with the active covered sensing. So the active covered sensing, the way we formulated it in its simplest form is again, the following diagram. So we have this closed loop that's an active hypothesis testing problem where you're trying to estimate the parameter theta, taking a finite number of values by probing and possibly adapting your strategy. But now we're going to introduce a second output to the kernel that gives you the samples. So the kernel also is a function of theta, the input action u. But then there's an output z that goes to what we call the detector. It's the adversarial detector. So think of it as it's a plane. So you're trying to illuminate a target to see if there's a plane or not. So theta tells you, if there's a plane or not, what kind of plane. And then zi is the plane itself, right? It has a detector. Okay, I'm being illuminated. And so one thing that's important to note is that our adversary is open loop. Okay, so the adversary doesn't have any input on the feedback link, right? So as the radar, we get to adjust what we do, but the adversary fundamentally is at a disadvantage because it doesn't have control over the feedback loop. To make the problem interesting, so in our case, we want to model something that we call active covered sensing. We need to define what it means to be covered. Okay, and so that's kind of what I want to highlight. There are these kind of cute, maybe niche information theoretic notions, but they kind of capture some cool problems. So to be covered, it means you need to define what it means to not be detected. And so we have to assume that there is one action, and I'm going to call it 0 for simplicity. That's my reference action, which means I'm not doing anything. So if you have a radar, it means you're not probing. You're not sending energy into your channel. And then you also need to explain that if you don't do anything, there's nothing useful that comes out of it. So we also have to assume that if you don't probe, you can distinguish the different parameters. Okay, so I have to be explicit about these assumptions, because if you give me a system where by doing nothing, I'm getting different samples or different distributions for different thetas, then it costs me nothing to estimate, right? So these assumptions, they're important to state, but they mean something physical, like from an engineering perspective. And we're also going to assume that the adversary is actually quite powerful. It knows theta, so it knows the state of the channel. I mean, the plane knows whether it's here or not, and it knows the strategy that's being used by the radar, right? So if the radar decides to do something smart and adaptive, this detector knows what's going on. And so how do you measure the ability of a detector to detect if you're doing something or not at the input? Well, you need to frame that as a binary hypothesis testing problem. The null hypothesis, this Alice, we call Alice the transmitter, does nothing, sends 0, versus Alice does something smart with a strategy. Okay, so here's the kind of thing that we can characterize, and I want to mostly highlight, what's standard and what's maybe not standard and what's intriguing to us. So I'm going to look at non-adaptive strategies. We have more results, but for simplicity, I'll just focus on the framing here for the simplest case. We're interested in characterizing the error exponents, right? And we're going to look at the worst case. Okay, so what is over all possible hypotheses theta I'm trying to discriminate for? What is the worst probability of error I can get? And I'm going to try to look at something that looks like an error exponent. And I think what the intriguing thing, if some of you are still following, is that I'm not normalizing by n, I'm normalizing by square root of n. And I think that's one key signature of my covetousness constraint, and I'm going to articulate why it's there, is that you can't normalize by n. If you normalize by n, you get 0. Essentially, it's telling you that if you want a positive error exponent in the traditional sense of normalizing by n, you get 0. Because the covetousness constraint essentially says, well, you should not be detected, so you really can't do much. But it turns out that they can do much means you have to use square root of n. And the second part here is my covetousness constraint, actually, which I'm going to explain in a few more details. I'm going to require that when I have used my strategy, worst case over all possible hypotheses I try to discriminate from, I want the relative entropy between the distribution on the output z's that the detector sees and a distribution that is induced when I don't do anything. Okay, so when I write pz given theta of 0, it's the distribution induced when I only send 0 at the input of my channel. So this is my reference doing nothing behavior. And this p with a boldface z here is the one that is induced by me using a strategy. And I want that to be less than theta. Okay, so I'll come back to the result. We actually have an exact characterization of the optimal exponent for non-adaptive strategies in that case. I want to talk about this because I think that if I want to convince you of anything, is that this is a fun constraint to work with. So why do I claim that this relative entropy constraint actually is something that you can view as a covetousness constraint? Well, suppose actually for very simple results. So if you have any test T of Z that you conduct on the sequence of observations Z that you obtain, there's a pretty standard result that says that there's a trade-off between probability of false alarm and misdetection that takes the following form. Probability of false alarm plus probability of misdetection has to be greater than 1 minus the total variation with a factor of 1/2. 1/2 norm 1 between the distribution that you expect when somebody is probing and the distribution when somebody is not probing. And using Pinsker inequality, you can relate that to a relative entropy. So when I say I want this to be small, it means I want this to be close to 1. Okay, so operationally and graphically, what does that mean? So let me use this curve here, because as you can see here, if I use relative entropy, there's a Pinsker inequality that's hiding somewhere. So there's some looseness there. So let's forget that for a second. Let's focus on using this metric here and see what it means in terms of an ROC curve. So you're plotting traditionally when you want to assess the performance of a hypothesis test, you look at probability of detection. So 1 minus probability of misdetection versus probability of false alarm. And any test has a trade-off curve in the plane, and it's actually in the upper left quadrant or above the diagonal. If it's not, you can always find another test immediately that has that property. So when we say that alpha plus beta, so really probability of misdetection plus probability of false alarm should be close to 1, what do we mean? We mean that the ROC curve should be close to that diagonal. Why does that ensure undetectability? Well, think about what's happening on the diagonal, especially the point 0, 0 at the bottom. It means probability of false alarm is 0, probability of misdetection is 1. Right, so how do you design a detector like that? It's a fire alarm that actually never triggers. Okay, so you never have a false alarm, but you never detect anything. So this is kind of pointless. If your detector has that performance, it's not doing anything. And similarly, the upper right corner, probability of misdetection is 0, probability of false alarm is 1. That's a fire alarm that's always ringing. So you're not getting anything. And in between, the diagonal is just an interpolation, probabilistic by flipping a coin between these two modes. So any detector that has an ROC curve that is on that diagonal means it's not doing anything statistically significant. And so if we constrain any ROC curve to have an ROC curve that is kind of squeezed close to 1, this is what we call covetousness, because you can do something very sophisticated, but it's not statistically relevant. Somebody can just do some random guesses and we'll get the exact same statistical performance. So that's covetousness. So when we use this relative entropy as opposed to norm 1, we introduce some slack. If you want a relative entropy that's less than delta, you're actually not controlling as finely the ROC curve. It won't matter for this talk, but I just want to mention that we're using this because it's simpler to manipulate. If you want to manipulate this, there's a bit more work that's involved, but this is actually the right quantity. Like if you want like a tight notion of covetousness, you should use this and not that, but that's it. So now why, so all that given said, there's that weird square root of n that showed up in my result, right? So why is there a square root of n? So think about what we're trying to say here. We're trying to say that you're forcing a statistical test on, you know what people are doing, the probing, and yet you should not be able to distinguish what they're doing from them doing nothing. So implicitly what that means is that whatever disturbance they include at the input of the channel with their probing strategy, it should somehow introduce a disturbance at the output that is statistically not detectable. And if you think about any test that you can run on a sequence of length n, think about, you're measuring the power, let's say. You can always form a very simple empirical estimation of the average power. And then you say, well, okay, that's just an average, how good is my estimator? You look at the variance, and the standard deviation is 1 over square root of n. So essentially, this intuition tells you that whatever disturbance you introduce, you will have to make sure that that disturbance stays within the statistical noise. And the statistical noise has the square root of n that shows up. So that's really why there's a square root of n, is because the amount of disturbance you can introduce has to be negligible compared to the power of the statistical estimator that you deploy. So that's kind of, so we've been playing a lot of this in many different situations, but what it does is it creates this situation where you have to normalize differently, and you have to look at all the quantities that you're used to analyzing in this very extreme regime where you don't do much, right? So for instance, if you were to do not just covered probing, but covered communication, you have to hide square root of n bits of information in a sequence of length n. And then it's not that easy to, we know how to do it, but you have to convince yourself that you have this very diffuse information content, and yet you can retrieve it, right? So here there's that same flavor. You have this very diffuse probing.
No, sorry.
Still have time, right?
Yeah.
You have this diffuse probing, and yet it's still useful for you to get something. And the answer is yes, yeah, it's still useful, but you take a huge penalty. Like your probability of error is going to decay like exponential minus something times square root of n as opposed to n. But we can say what exactly is that error exponent beta, and it's tight. So I want to highlight, this is the answer that we have. It's a bit unwieldy when you look at it. I just want to highlight that there's something cool about it that's very intuitive. So if you know channel of information, you recognize that it's here. That's a channel of information. Okay, technically the channel of information is this one here, because we have this active, we can choose the set of actions that we use. And even if we're non-adaptive, we can sample use from a fixed distribution. So potentially you can average your chain of information. So that's why there's this sum over u. You're averaging chain of information for a given input. But that's just the signature of our ability to control the channel input. Okay, so that's your chain of information. So that's to be expected. What's interesting is that you have that term here. So that term here is the signature of the covetousness constraint. So I'll explain in a second why you have a chi-square metric. It has to do with the fact that the chi-square is essentially this when you do a Taylor expansion. So you can't disturb too much. So if you look at a Taylor, like a first Taylor expansion of relative entropy, when you just say, okay, this cannot be too much different from that. So it's a disturbance of this with a little something. The little something will tell you that it's then multiplied by the first order in your Taylor series, which is a chi-square. That's where it's coming from. And the other little thing is that delta. So delta shows up here. So that may be another surprising thing I wanted to point out. In traditional information-theoretic problems, usually we have these strong converse results. Like they tell you, it doesn't matter whether you want delta or delta to be very small, or if you normalize, like the fundamental limits that we're after, they don't depend on these epsilon deltas. But here it does depend on delta. And I think that's also kind of fun signature of this covetousness problem, is that we're imposing constraints. You go back to my problem here. We're imposing constraints on not really the information embedding. We're imposing a constraint on the shape of the signal. And that's actually a much more stringent constraint. And so that usually there's no strong converse in that case. If you want your relative entropy, between the distribution you induce and your reference to be less than delta, and delta is 2 or delta is 0.2 or 0.02, it's going to change how much you can do. All right. So it's in a way, it's both more, it's a more fragile result, if you wish. So you have to set a predefined delta, and how big your exponent or how small it will be will depend on that delta. All right. So let me just highlight, how we go about proving this. And it's both, not complicated, and there are some subtleties. So we have to do two things. If you think about proving that we can find a strategy, because everything is non-adaptive, you actually don't have to worry about closing the loop. What you have to worry about is deciding, like a sequence of actions that you're going to use in open loop. Okay. And so you still need to make sure you can upper bound the covertness so that you guarantee covertness, and you want to kind of control the type of the input. So because you're covered, you can really not use a channel too much. Okay, so you need to find the right fraction of channel uses where you actually do something meaningful. And that fraction, as I argued before, it is like 1/√n. That's kind of the result. Then you need to show that you can achieve that exponent. So the kind of the cool thing that you have to do, or cool, I mean, intriguing things that kind of tricks we like to play with is, if you try like an ID strategy, you're not going to get anywhere. And the reason these kind of things don't work directly is because you're operating in that weird regime where the CLT kicks in, right? So you have to make sure that whatever you do, it's not enough to control the mean of your quantities. You need to make sure that you have a tight control of the variance. And so the way we do that is we use kind of a known trick in information theory. You look at certain sequences of a given type, but you need to define what these sequences are very precisely. So if you allow a fraction alpha of non-zero symbols, you need to make sure that when you define types, they have to be within some alpha times a small constant of your reference distribution P. And keep in mind, alpha decreases. So it kind of forces you to analyze, like all your traditional type results very carefully. And typically that involves things a bit more sophisticated than Hovding's inequality. I think the first time I talked about this, Max was in the audience and said, yeah, of course, use Bernstein's inequality because it gives you control of the variance as well. And so that's kind of exactly the kind of tricks we have to play with. Okay, so the converse is where you really get to understand why we have a chi-square distance that shows up. For the sake of time, I'm going to go a bit fast, but the way the converse works, you can't make any assumption, right? So you have to start saying I have a strategy. That strategy, you can do a like empirical average across time. It defines the probability that your strategy uses the symbol 1, sorry, a non-zero symbol. And then using traditional techniques, you can kind of get converse bounds on the probability of error. You can lower bound them as a function of the channel of information once you start focusing on the time instance where you're using a non-zero symbol. Remember, zero symbols don't give you any information. So essentially the converse, that the first part is a bit trivial. You're just saying, well, let me write my converse taking into account that even though I have n symbols, effectively I might use only a fraction 1/√n of that. So you get such bounds. But the second thing is to realize, okay, you need to satisfy the covertness constraint. And again, what you're going to say is you're going to take your relative entropy constraint, now that you know that you can only use a non-zero symbol, a fraction alpha of the time, alpha is very small, you do your Taylor series, and this is nothing, this first term here is nothing but a Taylor series of the relative entropy between this quantity here and your reference. And you immediately see that the alpha square goes out, it's upper bounded by delta over n. So alpha, your fraction of channel uses, has to be behaving like something as a function of delta, but most importantly, behaving as like 1/√n. And this turns out to give us the optimal constant. So we get the exact characterization. Okay, so that was my first illustration of kind of how you can use very traditional results to talk about things like covered radar. And some folks at MIT have built something like that. It's quantum, so it's more fancy, but it's the spirit of what they're doing. All right, so how much time do I have? 10 minutes? Okay. So the second vignette I wanted to highlight, which I think I got more excited about. It's more recent too, but I think makes a better case for why these models matter, is to apply that in the context of what people now call joint communication and sensing. So just to pretend that it matters for 6G, okay? This is my one PR slide. So I mean, there's real stuff that's happening. Like people are pushing towards millimeter wave systems, so very high frequencies. It starts to hit the frequencies where people traditionally do radar. And so if you're an engineer, you want to save money, save power. It kind of makes sense to have one hardware that does two things. So why not use the same hardware to do joint communication and sensing? And if you believe in vehicular networks, then they can talk to each other, detect that there are, targets in range. So, it's safer because you don't hit pedestrians. All right. So how do you talk about this problem? Say that again?
You said so you don't kill pedestrians.
Exactly. In Atlanta, it matters. This is not my picture, right? So they call it a target. So, yeah, so be careful when you create cartoonish, cartoonish description of the research, but that's not from me, okay? All right, so how do we talk about this in information theoretic terms? And so I promised that we tie to some of the comments that Aaron made earlier about, the need to maybe start thinking about beyond the traditional rate distortion problem. And so I'm going to make that case here. So there are some folks who've done some otherwise extremely nice work, but they've tried to model this joint communication and sensing problem with an approach that has this flavor of rate distortion. And so the way they model the problem is as follows. So they're saying, you have a transmitter here is trying to transmit a message through a channel. Okay, so that channel has one part that goes to your receiver. Your receiver has to get the message. The channel also depends on a state. I call that S. And you have a feedback channel, possibly noisy, that you have to use to estimate the state of the channel. Okay, so when you look at that model, you have feedback, well, close the loop. All right, so feedback does not increase capacity, but it's a bit more subtle than that. Aaron can attest to that. They are, so feedback can be very useful. So you would want to close the loop. So, but we impose a constraint that we care about decoding the message and estimating the state. Now, if you're an information theorist, what's very natural to do is to say, well, my state should be ID. Okay, now I'm going to argue quickly that in the context of this joint communication and sensing problem, whether you have a pedestrian or not is not ID. But if you do that, then it's very natural to measure your performance with two metrics. One is the probability of decoding error. The other is an average distortion. And this is great. And it's great in part because you can characterize the trade-off between the rate of communication and the distortion D exactly. Okay, so I'm not going to elaborate too much on the specifics of the result. I'm going to give you the spirit of it. And there are two great papers I encourage you to look at if you're interested. But essentially, the gist of the result is the following. It says, there's really no need to close the loop. Why? Because that state is ID, it keeps changing. So you closing the loop is not going to at all improve your ability to learn anything. The state keeps changing. So in a way, closing the loop here is useless. And what you should do is you should provision for a desired level of trade-off that you're interested in. What's kind of cool is that information theory allows you to start with these very high dimensional problems where coding over Bloch lengths and then goes to infinity. But in the end, the trade-off would characterize is in terms of quantities that are single letterized. They don't depend on n anymore. And the quantities of relevance here end up depending on one quantity only, which is the type of the code words that you transmit, their empirical distribution, or the histogram of their content. And so that alone controls the optimal trade-off between the distortion level that you have in your state reconstruction and the rate that you can push through reliably through the channel. Okay, so by the way, I was at ITW a few weeks back and there were folks from industry there. We talked about that, and for them, this is not necessarily a bad thing. Okay, I'm going to start questioning that model, but from an industry perspective, if you design a network, the idea that you have to provision for certain trade-offs is very natural. And from their perspective, what I'm going to argue next, which is this idea that, oh, no, you can do fine level adaptation. They're like, oh, no, we don't want to do that. Okay, that sounds scary and complicated, right? So one has to be careful. The reason I certainly don't mean to trash these results. They're actually potentially very relevant. But what I'm going to argue, though, is that this ID model, that's something that's really inspired from wireless. If you're trying to worry about a target, your pedestrian or your person on a bike is not going that fast. Okay, certainly they don't change at the rate of your symbol rate in 6G. And so it sort of makes sense to take a step back and start to think about the time scales over which the state is evolving. And we're going to do it by the extreme by saying S is not changing. Okay, so we're going to have a fixed standard state. What we're going to bring in is this ability to now learn the state S as we go. So in the interest of time, I'll keep that quick. But again, a lot of folks have done some cool extension of this ID model. But to us, the motivation was what's missing with the rate distortion theory approach is it's kind of an ad hoc information theoretic perspective on these problems, but it's kind of maybe missing the bigger point, which is what you're trying to detect moves slowly. And so you don't need this ID modeling assumption. And the moment you drop it, then it gives you the ability to adapt because you can learn. Okay, so credit where it's due again. There's another group, and Franz Willems actually was involved, that had similar ideas at about the same time. So our results were very similar in some sense. Okay, So what's the model that we're looking at now? So for us, it's the same model that I presented you before, except the channel state is fixed now. Okay, so now you can learn. Okay, that's a big difference. We're going to assume that S takes a finite number of values. So then the performance of your estimation can be measured in terms of the exponent of the probability of error. And try to do your estimation. Okay, so the encoder can use the feedback, the noisy feedback. So there's a delay, so you don't have instantaneous feedback, and your decoder is trying to estimate the message. So in the grand scheme of things, you could ask for a very complicated trade-off. You could say, I want to understand how fast my probability of decoding error decays versus how fast my probability of estimation error of the state decays versus how much rate I'm pushing through the channel. That's a three-dimensional trade-off. That's complicated. It's complicated because we already know that the trade-off between the rate and your the decay of your probability of message decoding error, it's linked, right? The further you are away from capacity, if you take some slack, you decay faster. So we wanted to remove that. So we're just going to ask for the trade-off between the rate of communication and the probability of detection error for the state. So we only care that the probability of decoding error is small, but we're not going to look at the exponential decay. That's for simplicity. So we have a trade-off between the rate R and the detection error exponent. Note that because of the setup here, where you have a fixed number of channel states, unless your kernel here gives you, no observation, any strategy, no matter how silly, will eventually allow you to estimate S properly, right? So it's important to look at the exponent to get an interesting trade-off. All right, that's what we want. We want trade-off between the rate of communication, R, subject to the constraint that you want to kind of decode correctly. So probability of error no more than epsilon, and your exponent for the probability of state detection is greater than E minus epsilon. And we want the trade-off between R and E, epsilon as small as you want. So in terms of terminology, it's good to start with a strategy that doesn't use the feedback. It's usually easier to analyze. I'm going to call that open loop. If I start using the feedback, I'm going to call that closed loop. And we want the trade-off. So in open loop, things are nice because we get an exact characterization. You don't use feedback, not too surprising. And again, we get this idea that so the result takes that following form. So the rate region that tells you the trade-off between the rate of communication and the exponent of your detection is a trade-off between a rate that's upper bounded by sort of the compound capacity type. And the exponent is that complicated function phi of px, but which is again just a churn of information. Again, you have this idea that because you're doing a joint operation, the behavior is linked through the same parameter, which is px, the type of the input code word, and then you can optimize over px. Okay, but because you don't adapt, you hit that minimum here. You have a compound capacity constraint. Okay, so we can characterize that exactly. What's nice is when you have something like that, you can ask yourself, what are good channels for which you don't have a trade-off? Like other channels for which I get the best of both worlds. It's as if I could maximize for rate and maximize for the exponent. And you get an abstract characterization, but it means your favorite additive noise channel satisfies that. So maybe practical channels actually don't really suffer from a trade-off. That's kind of the message. Again, here we have no feedback. So when we talk about feedback, so we did several things. You can try to close the loop. And when you close the loop, what it means is that suddenly the encoder can learn the state. If you learn the state, you can go a little bit beyond the compound capacity. Now you can be limited by the worst case capacity, which is a bit higher because it allows you to adapt your type of code word to the state that you think is the correct one. Okay, so that's one gain we should expect. But we wanted to think a little bit further and try to derive insights that are meaningful for engineers. Okay, so that was kind of really the motivation for us looking at these problems, trying to convince people that, hey, it's coming from statistics, it's very abstract, but it's actually relevant for the problems you design. And so we decided to cheat a little bit by allowing not just a fixed block length transmission, but a kind of a sequential setting. Like imagine you have a stream of data and you can packetize them. Okay, and we want to see like long term, on average, you're going to transmit over no more than n channel uses, but it's on average because you can do things sequentially and kind of sometimes, transmit a little bit longer, and maybe that's fine. But we wanted to bring in this ability of doing closing the loop and using a sequential detection strategies. But if you think about what we're trying to do, remember, once you start saying you need to adapt, you have this trade-off that you have to manage. You want to be reliable and you want to detect well. But to be reliable, if you're an information theorist, you know it's not just writing a mutual information. You need to code, right? And when you code, while you code, you can't adapt. And so you have this tension between the timescales over which you need to code for reliability, during which you can adapt, and then you can adapt on top of the packet. And so the key message that we have here is that when you have a fixed channel state here, and we believe that extends, under some mild qualifications to a slowly varying channel state, these two things can be compatible. Like as long as your channel state doesn't vary too long, you have enough time to code for reliability, and then you do an adaptation at the packet level. Okay, so let me get close to lunch. So I'm going to skip the details. So if you want to formulate exactly what it means to be able to sub-packetize and be sequential 2 minutes, you need to be very formal. So I'm happy to talk about that offline, but let me show you the result. Okay, so the result is that if you do that, then you get a much better trade-off. So there are two sorts of trade-off that kick in. First, improvement in the trade-off is that the moment you're sequential, you're not limited by the churn of information anymore. You're limited by the relative entropy, the worst case relative entropy between two possible states. But in general, that's higher than the churn of information. So you get a boost there. Second boost is if you close the loop, you're going to be limited by the worst case capacity, which is higher than the compound capacity. So to see that it's a worst case capacity of the compound, you need to decipher our expression a little bit. There's still a worst case. We're looking at the intersection over all possible states. But when we take the union, we don't take just the union over one possible code word type that we could transmit, because now we can adapt the code word type to the state that we perceive. So we take a union over all possible types that are function of theta. You don't have a single code book that you have to use all the time. You can have as many code books as you have thetas. And so that region is usually way bigger than the open loop, which didn't have adaptation, it didn't have sequentiality. And this is just illustrated here in an artificial example that shows you that the trade-off you get with the open loop non-sequential is dwarfed by the open loop, the closed loop sequential. But again, so the key thing that I want to convey is this takeaway that I think is meaningful for people who design this communication system, is that you should not try to adapt too fast. Most of the time, there's not going to be the need for that. And you will not really lose anything if you sub-packetize your data that gives you this unit of reliability, and you adapt the parameters of the code that you're using for reliability as a function of that feedback to improve your estimation. Okay, so pictorially, we divide our big transmission into small chunks. In every small chunk, you need a small header because you need the receiver to know what you're adapting. So you have to play these tricks, but the proof is extremely intuitive. It's what any engineer would do. Have a little packet, send some information as to what rate you're setting, what do you think the channel is, and then adapt that at the transmitter and keep that loop going. And it turns out that that's enough to give you the kind of very nice trade-off that you obtain here that gives you a boost. But so that's kind of our main message, is that forget about these ID models, which are very nice because they're connected to rate distortion theory, but unless you have super speedy pedestrian running here next to you, probably not so relevant. But then if you have something slower that you're trying to estimate, it gives you the ability to code, and you're coding very fast, so you get reliability and do a slow adaptation loop on top of that. And that seems to work as good as if you could adapt, at the symbol level. So I'll skip the details. I'll stop here. Thank you very much.
Quick question.
Okay, everyone's hungry.
Everyone's hungry. Thanks a lot, everyone.
How long